Swayam Prabha. Digital India. Educated India.
Hi, welcome again to the course of structural biology, and as I told earlier, this is the module where we have introduced the structural biology techniques. I have told about the introduction of the structural biology techniques, and now we are discussing X-ray crystallography. Today we will discuss crystal mounting. What is crystal mounting? You did everything and you get a crystal. Now you have to pick up the crystal and you have to put it on the machine, so that you get the diffraction. That is called crystal mounting. But before that, before crystal mounting, when you get a crystal, it is always not a happy news. So, how it works? You do the targeting, you do the cloning, you do the overexpression, you get the protein, then you set the crystals, and under the microscope you get to see a crystal, eureka. Sometime no, probably most of the time no. Why? Because when you are looking at crystal, it might be protein crystal, but it might also be salt crystal coming from the precipitant solution you have used to set up your crystals. So, how to check it? How to check the protein crystals? So, first you do the setup, you check crystals, then you go under microscope, and this is the way you see from smaller to bigger crystals are formed, and you get a single crystal. That is what our dream is. And now, how you know that this is a protein crystal? One thing, if you see this process, if you see actually your crystal is growing from this to this, have a journey, then you could say it is a protein crystal most of the time. But normally you get some crystals and you need to check, differentiate, it is a protein crystal or salt crystal. There are protein dyes, they are available and they only stain protein. So, if you put that staining and it stain the crystal, it is a protein crystal, it does not stain the crystal, it is a salt crystal. Crushing. Using a fine needle such as an acupuncture needle, crush a sample crystal. Salt crystal usually crush with difficulty into relatively few pieces, while protein crystal crush easily into a shower of very fine pieces. Remember, I talked about protein crystals are having a lot of solvent channel. So, it is soft, it is not like the crystal you imagine, it is not like a diamond you want to give to your loved ones. So, this is a very soft, and when you go through it you get the difference. If it is a salt crystal, it is very compact, so hard, and if it is protein crystal, it is soft. Dehydration. Allow a single crystal pick up from the drop and dehydrate in air, protein crystal will disintegrate, while salt crystal usually dry intact. So, protein crystal, because the solvent channel is a critical part of the formation of the crystal, when you keep it or allow it to dehydrate, it will disintegrate, whereas the salt crystal which is intact would keep intact. But you know, all those tests, my PhD supervisor Dr. Arnon Levy used to say, when you get a protein crystal, you know when you get to see the diffraction. So, that is true. Ultimately, it is the X-ray beam, the ultimate test when you throw X-ray beam and you get the beautiful diffraction pattern, that is the eureka time for a protein crystallographer. So, coming about mounting crystal, I talked protein crystals are extremely fragile, we have talked about this for multiple times. So, now it is in your head, protein crystals are soft and fragile, they may break upon certain contact with a solid object. the crystal remains in vapor diffusion contact with the mother liquor, if not it will dry out and crack. So, even if you have a crystal, now to transfer the crystal from crystal drop to the diffraction point, to the X-ray diffractometer, it is a journey which is helped by crystal mounting. Adjustable mounted cryo loop with easy snap microtube. So, this is what an ideal cryo loop is. So, what is the function of the cryo loop? I am explaining, but you know you have a crystal. So, you have to spoon it out. These guys are your spoons now. What they have? They have a distance from protein crystal to surface of magnet. They have a magnet here, because this magnet have to go and attach to tongue. I am going to show you the wand and tongue, what are them. Magnetic base of the pin, the microtubing, the neck of the loop which is the most important part. So, now if you see, this is a loop and this is going to pick out a crystal here, this crystal. The microtube is 24 millimeter in length and specifically engineered with easy snap. They have their own right about that, copyright. Notches at 10, 12, 14, 18 and 21 millimeter measures. So, different shape of the loops, and this is where the crystal is coming, this is where you make it with adhesive. I am going to show you that. So, this is the way we develop cryo loops. You have these loops, depending on what or how big your crystal is, you get the loop size. So, there are boxes like this. This is the box where you have different loop size. So, you get different boxes on different loop size. Then this is the magnetic base. This is a magnetic base. What we do? Nothing. We pick out the loop and put here in this place. You see, there is a hole, and then we put this, we call super glue. Super glue is a glue which could help iron or metal to be stick. So, you pick up the loop, you put it under the hole, you put super glue, and what you get is this. This is a complete loop. Now, as I told, so these are example of loops, and this is where you will have liquid nitrogen later, liquid nitrogen, and you put your crystal containing loop. We are going to show you that, and here you see there are loop coloring system on the loop base. So, red is 0.025 to 0.05 millimeter, green is 0.05 to 0.1 millimeter, yellow is 0.1 to 0.2 millimeter, blue is 0.2 to 0.3, like that. But that was old. Nowadays we use this. This is metal, and you do not have the color codes now. You have these boxes. So, you get these loops, you put it there, and you write behind the size of the loop. Okay. How cryo loop work? So, this is the crystal drop. You bring the loop, and remember, this is under the microscope. So, the crystals you cannot look in open eye. So, you look under microscope, you look at a drop, you see the crystal, then you bring your hand, you have to coordinate all these things. You have to work by looking under the microscope. We work continuously when we are actually screening crystals. We work for 6 to 8 hours, our eye pains and all these are all the hard work related to crystallography. So, you sit under microscope, you look at the drop, you look at a crystal, you try to scoop it, a lot of time you miss, then you scoop it, it is there, and then you pick it out. Okay. So, picking up a crystal by the loop, that is the process. Loop is necessary to pick up a crystal from the drop and avoid unwanted dehydration before freezing. When you are picking up, you see the mother liquor also comes here, and that saves the crystal. So, what next? But before telling what next, I am introducing some of the instruments. This is generally not in the course, but I try to introduce those things so that you get some practical knowledge of how actually protein crystallography could be done. So, this is tong. I am showing you how tong is working, and this is, you see, you hold the loop, this thing is the loop, you hold it with the tong. So, tong have a loop holder. Then you have a forceps which could hold the cryovial. The cryovial I have introduced. Then you have wand. Wand have this iron, and remember the base have the magnet. So, the wand actually hold the base, and in that way it hold the loop. This is the holding. Now, with these instruments I will show you what is mounting and cryo preserving the protein crystal. So, this is what liquid nitrogen holder. You could, these are very lightweight, you could take the whole liquid nitrogen and then you hold the cryovial, then you go under microscope, you scoop the crystal, and when you get the crystal, you put the crystal under freezing. When you are freezing, you might think that your crystal is getting hurt with liquid nitrogen, and yes, crystal could be hurt by liquid nitrogen. By hurt I mean damage. So, we use cryopreservation, I am coming into that. Now, you have the crystal inside the loop and you hold the wand, and in other hand in the forceps you have the cryovial. Now, you put the loop containing the crystal inside the cryovial, and now it is safe there. So, this is the process by which now you already save it. The cryovial contains liquid nitrogen. So, for some time it could be saved there, you could carry it in that way. If you are working inside the crystallography room, that is how we do in the home source. We hold this, we go to the crystallography machine and set them. But sometime or many time actually we have to go to synchrotron. So, I will talk about this later, but there are two type of X-ray sources which we use to solve crystal. One is the home source, okay, where in a institute you have your own machine, own X-ray diffractor machine, okay. Like in IIT Roorkee we have, in different institute they have their own home source. Home source are good, and I will talk about detail, but they have the limitation of, like, they take longer time. If you have smaller crystal, they cannot diffract, and the solution is synchrotrons. Synchrotrons are national facility. I will show about what you have advantage over home source and where are the synchrotrons are established. So, when you have to send it, like from IIT Roorkee, I have to send it to Italy. So, the saving is totally different. You see, this is called cane. So, these canes contain your cryovials with the crystals, and then you have this thing which is helping to put the crystals. So, you put that thing inside liquid nitrogen, and now you put the crystal there, you put the cover and you instead of that individuals, you now put the whole thing inside here and then you put it in a cryodeer. Instead of vial, this is a big container, and now when you put it there, it is safe for few days, even months. You could carry it to anywhere. So, now the question is, why freezing? Why you need freezing? Essentially, freezing eliminates X-ray damage to crystal. Crystal do not decay during data collection. Crystals must be frozen because water must be frozen to -70° very first to prevent the formation of hexagonal ice water glass forms. How? Crystal mounted on loops are flash frozen by dipping in liquid propane or freon at -70° or by instant exposure to nitrogen gas at -70°. So, if you do not do cryopreservation properly, what will happen? You will see this dirty diffraction data, and you see here you will see that ice is there. So, how you cryopreserve? There are many solutions which could cryopreserve: organic, non-volatile, non-detergent, osmolyte, polyols, polymers, solvents, sugar, salt mixture. A lot of things could be used as cryopreserver. And there is also a Hampton screen, which is the only screen available in the market which helps you to cryopreserve as a screen, but most of the time you will prepare your own cryopreserver. So, when you pick the crystal, now you come to the machine. This is a demonstration of the home source, and this is your loop, and you might have a question that I was talking about, that it should be under liquid nitrogen. So, where is the liquid nitrogen? So, this is where the nitrogen gas is coming out and keep the crystal cool. That is the process. Once you pick it there, you are not in the risk of losing your crystal. Okay. And this is the goniometer. Why goniometer is important? And this is the screen. So, goniometer mounted crystal is attached to a goniometer head for precise adjustment. Here you have something so that it could come and attach. Low melting hard wax is used to glue, or you could use plastic soil, which is available in the market. In many things are possible to glue it, and then you have to fix the rotations. Why fixing rotation is important? So, this is a goniometer head, here the crystal is, here the sample mounting screw, here the Z axis lock, here the Z axis adjustment screw, and this is a wrench. A wrench is used to adjust those things. So, y axis adjustment screw, y x axis lock, x axis adjustment screw, y axis lock, locking collar and sample mounting collar. So, when you have done the thing, you will lock them. Once a suitable specimen has been selected, it is securely attached to a goniometer head sample holder in an arbitrary orientation. That time you do not need to fix the orientation, but the goniometer head is then placed on the base of the goniometer assembly, and the crystal is optically aligned in the center of the incident X-ray beam using a video camera or a microscope. So, in the home source machine there is a video camera which will help you looking at the crystal, because remember the crystal would only be you could look under microscope. So, here it is projecting your crystal. So, you look at the crystal in the screen and you have to align the crystal. Why you need to align the crystal? Because you have the goniometer and the data you are collecting, you will collect at different angle. So, because there is automation, once you fix it, you do not need to fix the crystal after each angle of data collection. That was a older procedure where people have to do extreme hard work, they have to set up each and every angles. But we are fortunate now, we do not have to do that. So, once you set, you collect 90 degree, 180 degree, 360 degree and all. But to ensure the fact that with all the rotation your crystal would be aligned to the beam, because for getting diffraction you have your crystal aligned with the X-ray beam, that is very critical. The orthogonal X, Y, Z translation on the goniometer head are adjusted until the specimen is centered on the cross hairs of all crystal orientation. That is the most critical part. So, you see the X, Y and Z axis. The most common type of goniometer is a 3-circle goniometer, which offers 2 angle of rotation, the omega angle which rotates about an axis perpendicular to the beam and the phi angle about the loop or capillary axis. The third angle is fixed at magic angle of 54.74 degree with respect to the omega axis. The oscillation carried out during data collection involve either the omega axis or the phi axis. This is the centering. You see, when you have this, it is not center, you have to go for properly here. So, machine center is the intersection of the beam and the 2 goniostat rotation axis must be set by manufacturer. That to place crystal at machine center, rotate omega and kappa or different people say different names. So, I use that, you say kappa, you say phi, anything. If it moves from side to side, it is off center. If it is off center, we adjust the screws. Remember, I talked about the range, you use the range and adjust it and again check. Aligning crystal lattice to the beam, you see, rotate the crystal until the 0 layer disappears and the first layer is centered on the beam. You see here, this is misaligned, this is aligned. So, here 0 and 1 aligned. Concentric circles around beam means axis is aligned with beam. So, now you have the crystal and you have aligned and you do data collection. Now comes the thing which I have discussed earlier, irregularity in orientation or translation limits the order and usefulness of the crystal. You have nothing to do here, this depends on how the crystals grow. Okay. So, if it is if you look at its perfect order, rotational disorder and translational disorder. So, disorder destroy the periodicity. Irregularity in orientation or translation limits the order and usefulness of a crystal. So, you see, when it is perfect order, you get good diffraction pattern. When it rotational disorder, you do not get. When it is translational disorder, you do not get. So, disorder destroys the periodicity, leading to streaky, weak, fuzzy diffraction. These are, if your crystal is in perfect order, this type of diffractions you are going to get. Here you see that there is a portion which is not getting the diffractions. You know why? Because when you go back to the machine, you see that in the machine you set it and then you get the diffraction coming. So, when you are working, you do not want the diffraction to come, that is why you make it stop, but then you do not want the core of the beam to come and hit the crystal, so that it would destroy the crystal or would say burn the crystal. That is why there is a beam stopper, and because of the presence of beam stopper, you will see that these things are there. So, this is the effect of beam stopper. Now, when you have the diffraction pattern, you will start calculating the data analysis, and if you see, you will get circles which will tell you what resolutions you get data. Generally, if you look lower the resolution, you will get more dense spot, like you get denser spot below 3 angstrom, then at 3 angstrom you get good amount, and in the range of 2 angstrom you get less. After 2 angstrom, which is less than 2 angstrom, means actually higher resolution, you get even smaller spots. We will go for data analysis. We will look at the symmetrical pattern. Crystal symmetry leads to diffraction pattern symmetry. We will read about symmetry, and spacing of spots is used to get unit cell dimensions. So, we will also know about unit cells. So, what is our journey so far? We have done the target selection. We have done, like in crystallography, you have to do target selection, you have to do cloning, then overexpression, then the purification of the protein, then start setting up crystal. If you get a crystal, you go for diffraction pattern, you go for electron density map, and you get the protein model. We have talked about target selection, we have discussed cloning, we have discussed overexpression, we have discussed purification, we have discussed crystallization, crystal formation, crystal handling, and data collection. But in between crystal to diffraction pattern, we have things to discuss, then we will go for data analysis and model development. What we have, main thing is, we talked about X-ray crystallography, but we did not talk about the X-ray. Now, we will talk about X-ray. X-ray was invented by William Röntgen in 1895. When certain substances are exposed to the beam of a cathode ray tube, a new kind of penetrating ray capable of fogging photographic plates, even when shielded, was emitted. He called it X-rays. These X-rays also ionize gases through which they pass, and because of this invention, which have changed the world science, he was awarded with Nobel Prize in 1901, and remember 1901 is the year of first Nobel Prize. So, he got the first Nobel Prize in physics. So, we now know that how X-rays are produced, and especially how we could use it for X-ray crystallography. X-ray is when first moving electron slams into metallic object, it loses its speed, the kinetic energy is low, and then transform into X-rays. But how the machine works, what are the dedication of the scientists? When William Röntgen first invented X-ray, the first experiment he did on his wife, he put her hand and check how the image of bone is collected. This is the first X-ray diffraction experiment happened. So, those amazing sciences are there, those history of science, dedication of pupil, what is there, what is the principle, we will discuss it in the next module. In this module, we have discussed about the basics of structural biology, how we start to get the protein from where all the experiments should happen, how we get the target, how we clone it, how we purify the protein, and then you will come to crystallography for crystallization in NMR, in cryo-electron microscopy, in other low resolution technique. The basic part is same. So, we will discuss more on the next module. I will thank you for being an amazing audience. Please be with me in the next module. Thank you very much.